Hello and welcome. Today we are going to talk about recovering data. This is Marwan, Omar, Associate Professor of Cybersecurity and AI at Illinois Institute of Technology. So we are going to explain the techniques for hiding and scrambling information as well as how data is recovered. We're going to focus on three major operating systems: Windows, Linux, and Mac OSs. We are going to also learn about how to recover information from damaged drives. Let's start with deleting data. Simply deleting a file will not keep authorities from discovering it. Expect that evidence will frequently be deleted from computers you examine. So what this means basically is that if somebody deletes a file, it does mean that it is completely gone, because many people mistakenly think that deleting a file means it's irrecoverable or it's irretrievable. But in fact, deleting a file is not hard to recover. We have deletion, we have formatting, we have wiping out. So this is why we should expect that evidence will frequently be deleted from computers that we examine as forensic examiners, because perpetrators or criminals, they will try to delete data so that they can hide their tracks, and they want to keep examiners from seeing that data or recovering the data. Let's take a look at the file system and the hard drive. So we have clusters and we have sectors. The operating system views clusters, which are one or more sectors. The file system views clusters, which are one or more sectors. And then the hard drive divided into sectors of 512 bytes or 4096 bytes. So this is the internal structure of a hard drive. So it's divided or structured into clusters and sectors. Let's take another look here with the color codes. We have the red. This is a track. We have the blue, which is a geometrical sector. We have the red, C red here, which is the track sector, and we have the green, which is a cluster, which is a collection of units. This is how the booting system, the boot process works. So we have the operating system, which is stored on the hard disk. Then we have the master boot record. Then we have the boot sector. So the master boot record has boot codes, and it has this signature that maintains and identifies the partitions and a table of primary partitions. So let's say you have C, D, E, F, etc. And then we have the machine code that is loaded into the RAM. NTDLR, NTLDR loads the operating system during the boot process. So this is the boot process. We have the ntfs.system and ntoskernel.exe, and then the operating system is loaded. So this is all part of the kernel mode. Then we have the user mode, where user has access to applications like this presentation, for example, or any other applications that the user is interacting with. As we can see here, the FAT has a similar architecture to NTFS. The major differences are the OS loader and how the disk drive is organized. This is fast FAT. This is still ntoskernel.exe. So the major difference again is how the OS loaded and how the disk drive is organized. And this is an example of the computer management screen where, as we can see here, we have the system tools, then we have the event viewer, we have the shared folders, we have the performance, device manager, disk manager, and services. And here on my right, we can see here the volumes. So we have volume C, and the layout is simple. As you can see here, this is the NTFS, New Technology File System. So this is the default file system for the Windows operating system. So this is a Windows operating system. And as you can see here, the status here, this is healthy. It says system, boot, page file, etc. We have 74.53 gigabytes. We have the recovery partition, which is of the size 146 gigabyte. And this one is 73.06. Again, this is NTFS, New Technology File System. As you can see here also, this is the Access Data FTK imager. We're looking at the internal structure. We have the drive geometry, you have cylinders. So this is the number of cylinders, the number of tracks per cylinder. We have 255 tracks per cylinder, and then cylinders per track. We have 63 sectors per track, and then bytes per sector, 512 usually. Sector count is 7,913 and 472. So this is the logical structure of the drive, the physical drive information. This is the drive model, PNY USB 2 FD USB device, the drive serial number, the drive interface type. In this screen capture, we're also looking here again at the FAT. So we previously had, many years ago, with the older versions of Windows operating system, we had a file system which was called FAT16, file allocation table. That was the default file system for Windows operating system in the older versions of Windows. Then FAT32 came out, file allocation table 32, which was an improvement over FAT16, and now we have NTFS. But with this screen capture, we're looking at FAT32. As you can see, we have the root directory, we have the subdirectories. As you can see, some of them here, one of them is test FAT32. We have the unallocated space. We have also a partition, another partition that is formatted with NTFS, which is the New Technology File System. So you can see here, we have two different partitions. So one partition could be formatted with FAT32. Another partition is formatted with NTFS, New Technology File System. Here, the 8.3 file name is shown. As you can see, the long file name is internship, whereas the 8.3 file name is intern 1. This is the file name that Pat will use when looking up the file. So there's a long file name and there's a short intern 1. As you can see from the screen capture here, intern 1. This is the file name that the file allocation table will use when looking up a file. The master file table record number, which identifies where the MFT metadata file is located. We can see here some more information, and as you can see here, all of the file permissions, the encryption information, and security is all mentioned here. So this is NTFS, access control entry, ACE type, allow access. So this will allow access, inheritable, true. So there is a subfolder or subdirectory. SID, the name is called everyone, the access mask, the traverse folder, the list folder is true, creates folder, yes, true, create files, folders, delete subfolder and files, yes, delete, yes, read permissions, yes, change permissions, true or yes, and take ownership is also true. So Windows again had initially started with FAT16, file allocation table, and then FAT32, which was used in pre-Windows 2000 version. Then NTFS file system, it has been in use since 2000 actually. And it uses a table to map files to specific clusters where they are stored on the disk. With the file allocation table stored in a file in Windows, it will record the cluster number of the next cluster. It will add end of cluster if at end of chain, and then it will mark bad or reserved or open clusters. Deleting a file in Windows, when a file is deleted, data not removed from the disk, as we know. The file allocation table is updated to reflect clusters are no longer in use. Then new data saved to those clusters may overwrite the old information. So as we can see here, deleting a file does not necessarily mean that the file is gone, which a lot of people mistakenly think. The FAT is updated, so the file allocation table is updated to reflect clusters no longer in use, and then the new data saved to those clusters may overwrite old information. In TFS fundamentals, we have the master file table, which describes all files on the volume, including the file names, the timestamps, and so on. Then it serves the same purpose, obviously, as the file allocation table. It's just an improvement over the file allocation table FAT16 and FAT32. We have the cluster map, which is a map of all the clusters on the hard drive. Deleting a file in Windows, when a file is deleted, again, data not removed from the disk, clusters are marked as deleted and moved to recycle bin. When recycle bin is emptied, clusters are marked as fully available, and then the file name in the master file table is marked with a special character that means the file has been deleted. We have the disk dagger, which is a free and commercial. It has both free and commercial versions. The free version recovers one file at a time. This is a screen capture of disk dagger. This is another screen capture here. Another screen capture recovering an individual file using disk dagger. We have win and delete, which is another data recovery tool, easy to use and wizard driven. We select the drive and then select the file type and then selecting a restore file location. Where do you want to restore the file to? We also have free and delete, which is a free tool for personal use. The commercial version of this is also available. Free and delete, selecting a drive first. So then we have the Linux file system ext3, x4, storing a file. Linux stores files in contiguous blocks sometimes need to be extended. The exact size of blocks depends on parameters used with a command that creates the partition. It uses inodes and soft links. Deleting a file in Linux, the inode hard link is integral. inode links directly to a specific file. The OS keeps account of references to each hard link. When reference count reaches 0, the file is deleted. Recover the file in Linux. Here we move the system to a single user mode with init1 command. We use the grep to search for and recover files. The grep is a very important Linux command. -i -ab10 a100 forensic dev sda a file.txt. The output of the search will be written in file.txt. The ext and delete utility works with both ext3, ext3, and ext4 partitions in Linux. It uses shell commands. So an example here, to restore all deleted files from the SDA4 partition, we type ext and delete /dev SDA4 restore all. Scalpel works with Linux and macOS. Possible to compile source code to work in Windows. For the Mac OS and later versions are based on FreeBSD, a Unix clone much like Linux. Mac OS currently uses Apple File System APFS and Hierarchical File System Plus. MacKeeper recovers deleted files on Apple computers. It's a free, fully functional cloud version. This one has a free trial available. So this is the disk recovery tool. If we were to recover information or evidence from damaged drives, we remove the drive and connect it to the test system. We boot the test system, copy files from drive to test system, remove the drive, connect to test system, image drive, and then boot the test system. Is the drive recognized or not? And then perform repair, and then image the drive content. So we replace printed circuit board, we replace the read-write head assembly, and transfer the splatters to healthy drive. Recovering data after logical damage. Microsoft Windows has a utility called check disk. Linux has something similar called FSCK. Mac has another utility called disk utility. We have the sleuth kit and test this as well. Preventing logical damage, journaling the file system will help with that. Use a consistency checker, which is one of the tools that is available or built in by default. Use disk controllers with battery backups and use a system battery backup. Zero knowledge analysis means we are making a few assumptions about the state of the file system. The file system is rebuilt using knowledge of the undamaged file structure. Scan the drive of the affected computer, then match the results to the specs of a working file system. It's slower than consistency checking and can be used to recover data even when the logical structures are almost completely destroyed. So the file system gives the OS a roadmap to data on the disk. Type of file system on OS uses determines how data is stored on the disk. When you need to access a suspect's computer to acquire or inspect data, you should be familiar with both the computer's OS and the file system. Complementary metal oxide semiconductor CMOS. Computer stores system configuration and date and time information in the CMOS, which again is the acronym for complementary metal oxide semiconductor when power to the system is off. Basic input-output system or extensible firmware interface contains programs that perform input and output at the hardware level. We have the bootstrap process, which contains The bootstrap process contained in RAM. It tells the computer how to proceed. It displays the key or keys you press to open the CMOS setup screen. CMOS should be modified to boot from a forensic floppy disk or CD. So the disk drives are made up of one or more platters coated with magnetic material. The disk drive components are, we have the geometry, the head, the track, the cylinders, and the sectors, which is something that we just looked at a few minutes ago, as you can see here. And this brings us to the end of this presentation. Thank you for your time.